Well, good afternoon, students. As you can see in this video, I am going to attempt to teach the steps to the z-test for the mean using PowerPoint rather than the marker board. So what I want you to do is, after this first slide here, take notes. So copy everything from the following slides into your notes, and then you're going to use those notes to complete a problem on your own that I'll post on the website. This problem is also posted on the website. You don't need to then copy this PowerPoint slide down. The next slides, though, you'll need to copy. So as we can see, the problem here is, suppose you hypothesize that OSU students will, on average, have higher ACT scores than the national average. Now you go about testing your hypothesis by randomly sampling 15 students who are currently enrolled at OSU, and their ACT scores are as follows. So here we have the 15 students that we've sampled. Now you can obtain normative data from the ACT, or for the ACT, from the U.S. government, going to this website. And if you go there, you'll find that, at least for 2009, the mean was equal to 21.1 and the standard deviation was equal to 5.1. So we'll treat these values as population parameters to which we can then compare our OSU students. Now we'll answer this question, of course, using the z-test for means, because that's the only test we know right now. We'll learn some other tests in the coming weeks here. So the first thing we do is set up our two populations. It's arbitrary which population is population 1 and population 2. Here I set up population 1 as the general population, the norm. And so the mu, the population mean, is 21.1 and the population standard deviation is 5.1. Then population 2, OSU students. I don't know the population mean on the ACT for the OSU students. And then here, just a technical point, I assume the standard deviations are the same, so I don't really need to worry about those. I'm going to focus on the means. Are these means the same or are they different? Obviously, I'm going to need an estimate for this one. Where do I get my estimate? Well, here are some data. I'm not just going to make something up. So I've got 15 people here that are randomly sampled. I plug these numbers into my calculator or into SPSS or Excel or wherever you can get a mean, and the mean turns out to be 18.33. Now we go to writing our hypotheses. So the null hypothesis is the mu for the OSU students is equal to the general population mean, or they're unequal, either this way or that way, so the two inequalities here. So remember, we have all population parameters here, all mu's, no x bars. We have all possible outcomes covered, and they're mutually exclusive. And our prediction here, if you go back and read the question, it's stated in such a way that we're expecting the OSU students to have higher ACT scores on average than the general population or the norm. So that's our prediction here. The alpha level will be given in every problem, and most of the time I'm going to ask you to use an alpha of 0.05. That's going to be your p-crit. Sometimes I might ask you to use 0.01 or something different just to see if you can look something up in a z-table, but I'm usually going to give you an alpha of 0.05. Then all you need to do is just memorize, okay, z-crit is going to be plus or minus 1.96 because 2.5% is cut off by 196, negative 196 on this side, positive 196 on this side, so 5% total. So the darkened area here, the darkened region, is my rejection region. If I get a z-crit or observe a z observed value rather, up here or down here, I'll reject the null hypothesis. So by the way, if we look at our handout, we basically worked through all of this first page here. Now we're on to the second page where we can see we need the test statistics. So we need to get z observed. So we lift this formula off of the page and we're going to plug and chug through. So here's the formula. So I plug in 18.33, the mean for the OSU students. Here's my comparison mu, 21.1, and then 5.1 is the sigma. And then the sample size is 15, square root of 15. Again, what is this statistic called here, or this value, the standard deviation of the square root of n? That's the standard error of the mean. It tells me how spread out the means are in a sampling process. So I plug and chug through, and I get 1.32 for the standard error of the mean. Divide this out, I get negative 2.10. I then chart that, negative 210, in the normal curve. And I see that it is in the rejection region, just barely makes it across that threshold into the rejection region. So I reject the null hypothesis. And that's equivalent to saying the results are statistically significant. Again, this is what you're going to read in a journal article. The results are statistically significant. What do we conclude? Well, we conclude that the population mean for the OSU students is less than the population mean for the general population, or the norm. It's opposite of prediction. Now, why did we conclude this? Because 18.33, the OSU students, is lower than the norm, 21.1. So it's opposite of what we predicted. We thought we were going to see something greater than 21.1. Instead, we saw something less than 21.1. Now, as I said in the last video, or showed in the last video, I want you to write this out in words. So it appears that, contrary to prediction, the population mean ACT scores for OSU students is lower than the mean for the general population. So we hedge it a little bit, we hedge our conclusion. It appears that, because we really don't have mu, we only have an estimate for it. And then we look at the direction of the effect. Contrary to prediction, the students are lower, the OSU students are lower. And then we refer to the populations, because we're trying to make an inference here about a population parameter. We also want to look up the P observed, and we do that by going to our Z table, and we scan down the Z table looking for 2.10 as our Z score, and here we see it 2.10, and we want the smaller portion, which is 0.179. So we take this from our Z table, and then we're going to double that because we're looking on both sides of the distribution. So it's negative 210 or less, or 210 or higher, and the combined area there is 0.358. Now that is less than 0.5, which again leads us to declare it's statistically significant. So realize this is just two ways of doing the same thing. One way, I can look at the Z observed and compare it to Z crit, see if it's in the rejection region. If it is, I reject the null. I have statistical significance. The other way is I can take this Z obs and turn it into a P obs, a probability, and then I can compare that P obs to my alpha level or my P crit. And in this case, again, it's less than 0.5, so again, statistically significant. So it's just two ways of arriving at the same conclusion. Doesn't matter which way you do it, because obviously Z obs is related to P obs, just like Z crit is related to P crit. Now that we have that, we go back to our sheet, and we see that we want to move on to the effect size. So we lift the formula off the sheet here, and we go to the effect size. So here's the formula. Now we plug and chug through the 18.33, 21.1, the 5.1. That gives us negative 0.54. Oh, and by the way, just make sure that you're checking all these computations with your calculator so you know how to do all this basic math. You don't get hung up or stuck anywhere. We can take the absolute value of this and just use 0.2 as small, 0.5 as medium, 0.8 as large from Jacob Cohen. And we can conclude then that this is a medium effect using CCs, which means Cohen's conventions. And I'm going to talk more about these Cohen's conventions a little bit later. But right now, let's just go through the steps here. We've got a medium effect. We go back to our chart here, or our handout, and we see that the confidence interval is what we need next. So we'll lift this formula off the sheet. So our confidence interval, now first of all, this is the form that it will take. We're building the confidence interval around the mean for the OSU students because that's the mean we don't have. That's the mean we're trying to estimate. And instead of just using one value, 18.33 as my estimate, now I want to give you a range of values. So we plug and chug through the formula here. So we'll get 18.33, that's the mean. The Z crit, absolute value is 1.96. There's the standard error of the mean, which was from the previous slide. So you can just take that right from the denominator, from the previous formula, from the Z test. And now you get 18.33 plus or minus 2.59. You work that out finally, and you get 15.74 to 20.92. So I'm 95% confident that this bandwidth falls on or includes the true population mu, population mean for the OSU students. Now if we look at this, it is about a 5-point spread, and the standard deviation itself is 5.1. So we're going to go ahead and refer to this as middling precision. It's not incredibly precise, it's not incredibly imprecise, it's just kind of in the middle there. The bandwidth here is equal to the typical spread of the data, so we'll just say middling precision. That is it then. We are done with the problem. So in summary, what's happened here? We've declared we have a statistically significant finding. We have a so-called effect. And it appears that, what is the effect? Well, it appears that, contrary to prediction, it's opposite of what we expected. Population mean ACT scores for OSU students is lower than the mean for the general population, so that's a bit of a surprise. The standardized effect size, how big is the difference anyway? Well, it's medium according to Cohen's convention. So it's not a whopping effect, it's not a tiny effect, it's sort of a medium effect using Cohen's conventions. And then lastly, how precise is this study? Well, just middling precision. We only had 15 people after all, and so it would be surprising if we had a really highly precise confidence interval or estimate of that population mu. So it's a matter of, do we have an effect? What is the effect? How large is the effect? And then how precise is the estimate? All of this in quest of estimating a population parameter, in this case a population mean. So always remember, that's the essence of what we're doing here. Now whether that's what we really want to do or should be doing is a larger question, but that's where we're at right now.